Hi everyone, so in this video we're going to take those interaction diagrams that we just created and turn them into force diagrams, which are also often called free body diagrams. Now, interaction diagrams are very useful because they help us model and label all of the interactions between different objects in different situations. Now, we can use these interaction diagrams as a stepping stone to create force diagrams, which model all of the forces acting on a specific object or group of objects as we decide. And we're going to label these objects using something called agent-object notation, which we'll take a look at. These diagrams include more information than just the interaction diagrams, including the direction, which is indicated by the angle, and the magnitude or the strength, which is indicated by the length of the arrow. On the bottom, we have an example. From the first, we have the picture. In the middle, we have an interaction diagram. And on the right, we have our force diagram. So this is the process that we'll be modeling in this video. Why do we care about force diagrams? Force diagrams help us solve problems by allowing us to add together all of the forces acting in both the horizontal and vertical direction. This will become incredibly important, especially when we have multiple forces acting on the same object. In order to begin adding forces, we'll first define our coordinate axis, choosing a positive and negative direction. I've labeled mine in the upper right-hand corner. I'm choosing up and right to be positive. When I write out the sum of forces, I'm going to use an uppercase sigma, which is a Greek letter, and I'm going to look at all of the forces in the x or horizontal direction separately from the y or vertical direction. So in this example on the right, we have two people pushing on a box, and let's say this box is on the ground. So I'm going to label these forces using our agent-object notation. So what I've done is I've drawn in all of our forces. We have the normal force here, which is the force that the ground produces on the box. We have we call the person on the left person A. We have this force, which is the force that person A exerts on the box. This force over here they're both contact forces, right? This is the force that person B exerts on this box. And then we have our gravitational force down here. That is the force that the Earth exerts on the box. So if I were to add up these forces, I would begin just by looking at the horizontal and then separately at the vertical. We never mix them together. Okay, so let's take a look at the horizontal direction. What forces do I have acting horizontally? Well, I have the force of person A on the box. That's going to be a positive because it's pointing to the right. And I have the force of person B on the box. That's going to be negative because it's pointing to the left. So down below, I'll write my sum out like this. And in this case, because I know the actual values or the strengths of these forces, I could even quantify this like so. So I know that the sum of the forces in the x direction would be 50 newtons to the left, or negative 50 newtons. Now I can repeat this process to find the sum of the forces in the y, or the vertical direction. My normal force, or the force that the ground exerts on the box, is pointing upwards, so that'll be positive. And my downward force, the force that the Earth exerts on the box, is going to be negative because it's pointing down. So I can write my sum out for the y direction like this. I can quantify this just like before as well. And notice that the sum of the forces in the y direction in this case is 0. So in other words, there is no net force in the y direction. We only have a net horizontal force. This will be important later, but for right now, just take a note of it. And there we have it. Now, we're going to use this later when we do calculations, but it's important right now just to know how to do the sum of forces. So all you have to do is add up all the forces, keeping track of negative signs, and you have your sum of forces. That's all. Let's apply this to the series of examples we looked at before for interaction diagrams. All right, so if I look at the interaction diagram we drew for the little pug on the ground, if I want to draw a force diagram for the pug in particular, what I would do is draw a circle with a dashed line around the pug to indicate that the pug is going to be my system of interest. The system is the object or objects that we are choosing to look at for the purpose of our diagram. So I'm going to go ahead and circle the pug. And now, to draw my force diagram, I can simply take a look at all of the forces that cross that boundary that I've drawn. I see that the gravitational force between the pug and the Earth crosses that boundary, and the contact force between the ground and the pug also crosses that boundary. So I know that on my force diagram, I'm only going to have those two forces. So to begin drawing my force diagram, I'll show a box on the right, and inside that box, I'll write pug, because we're looking at all of the forces acting on the pug. Then I'll show the two forces I identified earlier, gravity from the earth and the contact force from the ground. Now I know gravity is going to point down, so I'll show that with a downward arrow, and I'll label that force earth on pug. This is what we call agent-object notation. The earth is the agent, or the thing exerting the force, and the object is the pug, or the recipient of that force. And then I know that in this case, since the ground is pushing back up on the pug, that arrow will point up, and I would label that F ground on pug. I can also write out my sum of forces. The sum of all the forces in the x direction in this case is 0 because there are no forces in the x direction. I only have 2 vertical forces. And the sum of all the forces in the y direction could be written as, well, this is a normal force and this is a gravitational force, as the normal force minus the gravitational force. And in this case, I know that these two forces are equal to each other because the pug is not accelerating in the vertical direction. All right, let's take a look at another example. All right, so we have our interaction diagram for our Olympic gymnast here. And let's say we wanted to do a free body or force diagram for the gymnast. I'll begin by showing a system boundary or a dashed line around the gymnast on my interaction diagram. And then I'll take a look and see how many forces cross that boundary. Well, I have the force of gravity between the gymnast and the earth. I have the force of tension between the gymnast and the left ring. And I have the force of tension between the gymnast and the right ring. So I know I'll have 3 forces on my force diagram. To draw my force diagram, I'll draw a box and put gymnast in the middle. And I know, as always, that the force of gravity on the gymnast is pointing straight down. And in this case, since the rings are keeping the gymnast suspended in the air, they must be pulling him upwards. So I'll show 2 forces pointing up, one from the left ring and one from the right ring. All right, and I've got an abbreviated left and right ring like so. I'll conclude by summing all of the forces in the x and y direction. In this case, I don't have any forces in the x direction again, so I know the sum of the forces in the x direction will be 0. But I do have 3 forces in the y direction, right? The rings are creating positive forces upwards on the gymnast, and the earth is creating a downward negative force. So I can write out the sum of forces in the y direction like so. And because I know the gymnast is not accelerating again vertically, I know that those 2 forces upwards will balance the force downwards. So there won't be a net force in this case because the gymnast is not accelerating. He's standing still. Let's take a look at another example. So let's say that I wanted to draw a free body diagram for the bowling ball. Take a moment, pause the video, and see if you can draw a force diagram for the bowling ball based on our 2 previous examples. I'll begin by drawing my system boundary, and I see I only have 2 forces acting on the ball, the normal force from the floor and the gravitational force from the earth. On my force diagram, I'll show the force of gravity pointing down and the force from the floor pointing up. And since the ball is not accelerating vertically, I know these 2 forces must be balanced. Now, be careful. It's very common that when an object is moving in the horizontal direction, I will see students show a force like this in the direction the ball is moving. Is there anything causing this force after it's left the bowler's hand? The answer is no. Every force has a source. And since the ball is no longer in contact with the bowler's hand, there cannot be any contact force between the person and the ball after it's left their hand. So even though this ball is traveling to the right, it is not accelerating to the right. And therefore there is no net force causing it to accelerate in that direction. Once it's left the bowler's hand, it travels at a fairly constant speed, ignoring any friction. Therefore, we will not have any forces in the horizontal direction. Please make sure you take special note of this, as this is a very common misconception that students have. Since this diagram is essentially the same as the pug sitting on the floor, we won't show the sum of forces. You can refer back to that diagram for that. Let's take a look at another example. Now for this example, let's create separate force diagrams for both the person and the dog. Pause the video and see if you can write out the force diagrams for both of these objects. Okay, I'll begin by writing out my system boundaries. And so I see right now I have 3 forces acting on the person. We have the tensional force from the leash, the normal force from the ground, and the gravitational force from the earth. And I also have 3 forces acting on the dog, the normal force from the ground, the tensional force from the leash, and the gravitational force from the earth. Notice We've neglected friction here, and I'm doing that on purpose. We're going to have to revisit our diagram and add friction, but we'll see why in just a moment. For right now, let's write out our force diagrams given the forces that we have shown on our interaction diagram. I'll begin by labeling the force of gravity acting downward on both objects, and the normal force from the ground acting upwards on both objects. All right, now I have one more force that I'm aware of, and that's the tensional force from the leash. Now, I'm going to draw on the diagram I have on the left, the picture. The person feels the pull from the leash in this direction, right? They're feeling their body being pulled to the right. So on the person's free body diagram or force diagram, I'm going to show this force pointing in the same direction that the leash is pulling on them. So at the same angle and pointing in the same way. So it would look something like this. So I've drawn that in on my force diagram for the person and labeled it the force of tension that the leash exerts on the person. Now for the dog, you might imagine this will act in the opposite direction, right? The dog feels the leash pulling him upward, like so. So I'll show it on the dog's force diagram in that same direction, like this. All right, so now that we think we have all of the forces on our objects, we have to ask ourselves, would these objects be stationary? Now, the man and the dog are not moving, right? Their forces are balanced, and so both of them are standing still. But if we look at our force diagrams, what do we notice? For the person, I have a force pointing in the right direction, right? So to the right. It's not horizontal, but it's got some part of it that's horizontal. If there was nothing else acting on this person horizontally, what would happen to them, right? Well, they would start to accelerate to the right. They would fall, essentially. So I know there has to be some force over here that's helping the person not be pulled forward. Now, similarly for the dog only has a force pointing to the left, right? So there must be something pointing to the right for the dog. Otherwise, the dog would be pulled backwards. This is how you know there's friction in this scenario. If you're ever not sure if there's friction, draw your force diagram and system diagram without friction, and then ask yourself, should the objects be moving? Are they moving currently? In your force diagram, if they look like they should be moving, but you know they're not supposed to be, friction will help make up for that difference. So friction always acts opposite the direction that an object is moving or would move if it were. So let's add friction to our interaction diagram. I've showed that interaction between the ground and both the person and the dog, and we'll also draw in an arrow pointing to the left for the person and the right for the dog. I've also gone ahead and moved the force diagram for the dog below so we have more space. The last thing we need to do is sum all of the forces in the horizontal and vertical directions. Now, it's important to note that because this angled force right here, the force from the leash, is not horizontal or vertical, we have to split it into components first to be able to find the sum of forces. If I were to show those components in blue, the horizontal component would look something like this, right? And the vertical component would look something like this, where this is the force of tension in the y direction, and this blue arrow would be the force of tension in the x direction. If I were to redraw my force diagram, I would have it look something like this. It's always a good idea when you have forces acting at angles to redraw your force diagram before solving for the sum of forces. Now, I have my force diagram complete. I'll go ahead and look at all of the forces acting in the y and x directions, adding them together, being careful about negative signs. My sum of forces in the y direction looks like this, and my sum of forces in the x direction looks like this. Now, when it comes to the force diagram for the dog, if I were to draw the angled force as components, it would look something like this, right? This would be the horizontal component of the tension force, and then this would be the vertical force, or the vertical component of my leash force, the tensional force. So I would redraw my diagram showing an upward arrow for the force of tension on the dog, and the leftward arrow showing the horizontal force of tension on the dog. I would sum the forces then the same as the person. So I know this was a very complex example, but this is essentially as complex as it gets. So please pause the video, take a moment, and make sure you're comfortable solving problems like this. If you have a question, right now would be a good time to call me over or speak to a neighbor before proceeding. All right, for one final example, let's draw out the force diagrams for both blocks A and block B in this scenario. Take a moment, pause the video, and see if you can write out the force diagrams for both blocks on your own. Okay, now I began by drawing the system boundary for both blocks separately. And in this case, we can ignore friction. So I see that on block A, I actually have 4 arrows pointing into that system boundary, or in and out of. We've got the contact force from the hand. We have the contact force from block B. We have the gravitational force from the earth. And we have the normal force from the table. So I know that on my force diagram, I'll have those 4 forces. Now on block B, we only have the contact force from block A, right? We have the normal force from the table, and we have the gravitational force from the earth. So I'll go ahead and write out my force diagrams using those forces. So I've drawn out my normal force and my gravitational force on each block, which is fairly straightforward in this case. Now when it comes to the contact forces, on block A, the block is being pushed to the right by the hand, right? The hand is pushing the block to the right. So on block A, I'll show that force from the hand pointing to the right. Then in the case for block B is being pushed to the right, and block B feels like block A is pushing it to the right. So that contact force between block A and block B, we can show that pointing to the right on block B, right? Now, there's one more force we have to draw in, and that's the force of block B on block A. Now, we talked about Newton's third law, right? For every force, there is an equal and opposite force. What does that really mean? Well, we talked about the idea that forces come in pairs. So right here, if block A is pushing on block B, and the block B feels it pointing to the right, then block A must feel a push back from block B in the opposite direction. It's just like if you push a wall, the wall will feel pushed in one direction and you will feel pushed backwards. So I can show this as a leftward pointing arrow on block A, like so. And on my diagram, I'm going to circle the Newton's third law pairs in red. Once again, a Newton's third law pair is no more than a pair of objects that interact with each other. So in this case, block A pushes on block B, and block B pushes back on block A. Now, it's very important to notice that the normal force on the table and the gravitational force are not Newton's third law pairs. Even though they're acting in opposite directions, and in this case they are balanced and equal, they are not Newton's third law pairs, right? They don't happen between the same objects. This normal force is between the table and block A. The gravitational force is between the earth and block A. For two forces to be considered a Newton's third law pair, they have to act between the same two objects. So in this case, we have the force from B on A and the force from A on B. So just keep this in mind because you may be asked at some point to identify the Newton's third law pair if there is one on a force diagram. So just make sure that you're looking for two forces acting between the same two objects. If I were to then write out the sum of forces in the x and y direction for both blocks, it would look like this. Take a moment, pause the video, and make sure you feel comfortable with this problem before moving on. We'll conclude with a look at how the force diagram would be different if we considered blocks A and B to be one large block, block AB. Take a moment, pause the video, and see if you can draw the force diagram for this scenario, like before. I'll begin by drawing my system boundary. Then I'll draw in a force diagram, given that we have three forces acting on the sum of the blocks. We have the contact force from the hand, the normal force from the table, and the gravitational force from the earth. So this actually simplifies the problem quite a bit because we get to ignore that internal force between block A and block B, right? That Newton's third law pair. So if you're ever asked to solve for perhaps the acceleration of the two blocks together, this might be a nice approach to consider them to be one large object and simplify our force diagram. But we'll learn more about that later. For right now, let's go ahead and finish by summing the forces in the x and y direction. Alright, and that concludes our series of videos on drawing interaction and force diagrams and writing out the sum of forces. Please take a look at the interaction and force diagram exercises on Canvas to continue practicing this skill.